Hello, this is Dr. Gardner. We'll be talking about density today. First of all, if we consider the property that is density, we would categorize it as a physical property. I can identify the mass of a substance as a physical property because it doesn't involve a change in the identity of that substance as it might go through a chemical reaction from one substance to another. I don't have to have a chemical reaction at all in order to determine the mass of my substance. I also can determine the volume of my substance. If I look at those two different physical properties, neither one involves a change in the identity of the compound that we might be looking at. So if I take a ratio of my mass of my substance divided by my volume of the substance, we determine densities. So density, since it results from a calculation that includes physical properties, is also a physical property. So we'll be doing some calculations today with respect to density, but first of all, before we begin that, we're going to look at some comparisons of common densities for substances that are in the world around us, and how that relates to where substances might find themselves in positions on a density column. So we'll be looking at what a density column is. We'll also be solving some calculations for density or mass or volume with respect to any of the variables we might be interested in. You should be very comfortable with solving for any of those variables in calculations involving density. We'll also determine how to find the unknown identity of a substance by using its properties of density as well. Now, if we start to compare what density is, realize that it's just a ratio of mass over volume for the substance you're looking at. Now, it doesn't matter the size of the sample I have. I could have a very small sample of the substance I'm studying or a very large sample of the substance I'm studying. The ratio of mass over volume in both cases would be identical. If it's the same pure substance, I should get the same value for density in those cases. So we can write density in this following equation. Density is equal to mass over volume. Frequently in the course, I'll just write a D for density is equal to an M for mass divided by a V for volume. So if we consider the densities of different states of matter, solids, liquids, and gases, well, the most common densities that you run into for solids would be grams of my solid for every centimeter cubed. But remember that my 1 centimeter cubed is merely 1 cc or 1 milliliter. So if I see a density for a solid reported in grams per milliliter or grams per centimeter cubed, it's going to be the same value for the two because there's a one-to-one relationship for those volume units. Now, if I start to look at liquids, well, liquids have a ratio usually of grams per milliliter. Now, realize that gram per milliliter is the same as a gram per centimeter cubed. So why might we see more liquids reported as grams per milliliter? First of all, think of the measuring device you might use in order to determine volumes. Perhaps you might use a graduated cylinder in the lab, or you might use a burette, or we might use other types of glassware that has graduations on it with respect to volume in milliliters. So it's very common that liquids have volumes measured in milliliters and their mass measured in grams, and so their density is reported in grams per milliliter. So that's very common to see. Now, if we look at gases, though, we'll find that we're not using centimeters cubed or milliliters. Because gases have such a low density, meaning that they have very little mass per volume, we often report units for gases in density of grams per liter. Now, the reason we do this in order to get values for gas densities that are large enough that they can be compared to other substances for magnitude, we need whole liter quantities. That's because there's so much empty space between particles in the gas phase, right? My atoms, molecules, ions, those particles in the gas phase has all this empty space between them. You could say gases are really space hogs, right? So because of all that empty space, there's very little mass per every specific volume of that gas. So in order to get gram quantities, usually we report in grams per liter. Okay, so that's pretty useful. Now, we can realize that if we compare densities of solids, liquids, or gases, there's a general trend that works most of the time, but not all of the time. The density of solids is frequently greater than that of liquids, so I'm going to show you an exception to that here in just a moment that we'll talk about. Realize, though, that both solids and liquids are much, much more dense than gases, which have so little mass per volume because of all the empty space between the particles in the gas phase. So that's something general to remember. Gases will always be much less dense than liquids or solids. Frequently, liquids will be less dense than the solid counterpart to that substance, but there are some exceptions. For example, the most common one you probably think of is a very abundant substance on planet Earth. That's going to be dihydrogen monoxide, also known as water. So if we consider water in its liquid state, it actually in this case happens to be, it happens to have the liquid be more dense than the solid. So we've reversed that trend slightly, and we can see that the ice cubes happen to be floating at the top of the cup. In fact, you probably would be shocked to see ice at the bottom of the cup. If that were the case, we'd imagine this probably isn't pure H2O. There's maybe some other liquid present in the solution, or we might end up having isotopes, like if we had an ice cube made out of D2O, deuterium, or the hydrogen isotope that has two nucleons in the nucleus, meaning a proton and a neutron, the ice cube would actually be denser than the surrounding water with a hydrogen 1 isotope. So we could actually see in the case where we talked about isotopes, the hydrogens would be at the heavy water isotopes of D2O, and the D isotope would be at the bottom of the glass. So here we're kind of seeing a case where we break this general rule. Now, most other liquids, when I freeze them, have the solid become more dense, so we would see that ice at the bottom. Now, we might consider that we're fairly lucky on planet Earth that the density for ice is less. This probably contributed to erosion of rocks to produce soil, because every time water would freeze, it would expand and break the surrounding rocks up into finer soil, and then it would thaw and refreeze, and that would continue to break up rocks into fine soil for plant growth. So that was probably very important for planet Earth. Also, if you can imagine, if lakes or bodies of water were to freeze, the ice forms on the surface, which kind of insulates the water on the bottom and allows aquatic life forms to still survive. If this weren't the case for water, if water was actually more dense in the solid state for the ice than the liquid state, we would probably imagine that the lakes and rivers and bodies of water would freeze from the bottom up, and all the aquatic life forms would end up frozen as well. So this is probably very important that water has this unique property that the solid is less dense than the liquid, which allows many useful things to occur with the potential development of life on Earth. Okay, so just remember, ice is an exception to this general rule. Now, if we look at a picture of this, we can see that if we have water molecules, they tend to be fairly disorganized, moving past one another. It's a condensed state of matter, meaning the density is fairly high because the molecules are in close proximity to one another, but they're fairly disorganized. When water freezes, we find that the hydrogens in the water molecules, which are slightly positive in the molecule, will be attracted to the slightly negative oxygen end of the molecule, and this forms nice hexagonal arrays or channels in my ice. This causes the spacing between the water molecules and the ice to become slightly further apart on average than the water molecules in the liquid. This causes us to have a lower density solid state, which allows the ice to float on top of the water. It's just something kind of interesting to notice. So we can thank hydrogen bonding, which we'll talk about more later in the course, for the result of this less dense form of ice compared to liquid water. Very interesting when we look at the structure down at the individual molecules. Now, a really fun density that your instructors might want to do with you is to go ahead and get a container filled with water, and if they have a standard soda and a diet soda, or if you can get these at home and put them in a container of water, you're going to see something kind of surprising. When I put the two into water, the standard soda will actually end up sinking and the diet soda will float. So there's a difference in density of the two. Now, if we know the density of water is 1.0 grams per milliliter, or 1.0 grams per centimeter cubed to two significant figures at 25 degrees Celsius, well, then this tells us a bit of information about the sodas. So we know when we have the sugar dissolved in standard soda, it ends up being a little more dense, so it would sink to the bottom in the water. If it was a little less dense, we'd end up with the diet soda, which has a lower density, would float on top. So that tells me that the standard sugared soda has a density greater than 1 if it's below the water. If we have the diet soda, we have a density that's less than 1, which would cause it to float above the water. So we're noticing that we have, from highest density to the lowest density, a simple density column. The highest density is the sugared soda. The intermediate density would be the water, and the lowest density would be the diet soda. Okay, so that's the order that we would have here. So we can make some general predictions, so that's pretty useful. Okay, so it might be a fun little experiment to do at home if you want to compare sodas. It also would help you if you're at a party and you wanted to have standard soda rather than diet soda. You probably want to reach a little further into that ice cooler and get the sodas at the bottom. Whereas if you'd rather have a diet cola, you probably would want to reach at the top. Okay, now that we realize that we can make a density column with higher densities at the bottom, intermediate densities in the middle, and the lowest densities on top, we can look at other types of density columns. Let's compare some of these here. So I've shown a simple density column that shows you that honey is more dense than Carol syrup, which is more dense than Dawn dish soap, which is more dense than water, which is more dense than vegetable oil, which is more dense than rubbing alcohol, which is more dense than lamp oil, and all of these are more dense than the gases in the atmosphere above the column. We can also see in this case, this is a really fun density column that shows your difference in densities. Mercury has a fairly high density of 13.6 grams per centimeter cubed. It's at the bottom of our density column, and we notice that copper has a density of 8.8. So the copper wire is actually floating on top of the liquid mercury here. That means we could also take something like if we took a post-1982 penny, which had composition of mostly copper, it would float on top of the mercury. Okay. Now we could take corn oil, which is less dense than both the mercury and the copper. It would layer next. If we take a rubber washer with a density of about 1.34 grams per centimeter, it would layer on top of the corn syrup. And then if I take glycerin with a density of 1.26 grams per centimeter, it would be on top of the rubber washer and the corn syrup. Then we see a tar ball here is floating on top of the glycerin. It has a density of 1.02, which is just slightly greater than that of the water above it, with the density of 1. So here's our water layer. Density of 1 is a nice one to memorize. This is the only density for the course you will need to memorize, is that water's density is 1 gram per centimeter cubed at around room temperature. Now, however, you do not need to memorize all these other densities that we're working with. You will always be given them on a test or be able to look them up in your textbook. Now we can see that some types of plastics, depending on the form of plastic that we're looking at, is less dense than water. So here we have a plastic component that's 0.93 grams per centimeter cubed, so it's actually floating on top of the water. Now thinking about that, if I threw cardboard into water, it probably would float on the top. So what do you think the density of cardboard is? I hope you think that it's less than that of water. So we'll see later on a calculation where you'll try to prove that to yourself. Okay, so here we have corn oil. The corn oil is less dense than the plastic and the water, so it's floating on top. Then I have a piece of wood that's 0.7 grams per centimeter cubed that's floating on top of the corn oil. And then I have the air in the atmosphere above everything else, where I start to deal with densities that are much smaller than this. Okay, very interesting density columns. Now I had to share kind of a little bit of an interesting picture with you with respect to density columns, and that's a picture here where we look at lithium metal floating on corn oil, which is floating on top of water, and then we have our nice little friend here, the fish. Now I think this is a really fun demonstration of a density column, because there's a little bit of jeopardy involved, because that fish could be in danger if that lithium metal hadn't been light enough to float on top of the corn oil. Now your alkali metals in group 1 are quite reactive. They will react with water fairly violently in an exothermic process that will release hydrogen gas, when it can produce sparks which might ignite the hydrogen gas and cause an explosion. In fact, as we go down the alkali metals in your group 1 on the periodic table, you have lithium, sodium, potassium, rubidium, cesium, francium. They become more reactive as I go down. Now lithium, even though it's the least reactive of the alkali metals that we're looking at with respect to its reactivity with water, it's still quite reactive. So I actually think our friend the fish here is probably pretty happy that the lithium metals has a low enough density that it's in the corn oil at the top of the density column rather than in contact with the water layer. So if we want to look at the densities of these, let's look at the air at the very top of our fishbowl. Very top of our fishbowl, we have air at a density of 0.0013 grams for every centimeter cubed. And then if we look at the lithium metal, well, it has a density of 0.534 grams per centimeter cubed. Do you notice the air's density is very low? Remember what we said about often the units for the density of air are reported in grams per liter. That would give us a larger value, but I do have to look at volumes that are liter volumes rather than centimeters cubed volumes. Remember, there's 1,000 centimeters cubed or 1,000 milliliters in 1 liter, so that you have a much larger volume, 1,000 times the amount described here, so the mass would be 1,000 times that displayed. So that starts to get you up to 1.3 grams per liter. Okay, so you'll often see gas densities in grams per liter. Their values may look comparable to solids or liquids, but realize the units are not the same, so you'd have to do a unit conversion to actually compare the two densities. Okay, now if we consider the corn oil has a density of 0.921 grams per centimeter cubed. So it is more dense than the lithium, and it's more dense than the air, so it's the next lowest on our density column here in the fishbowl. And then we were told to memorize that water's density is 1.0 grams per centimeter cubed, so it'd be at the bottom of our layers in this simple density column. So these are kind of fun to look at. We can also use this concept of different densities and how they layer on top of one another if they don't mix together. Now realize some liquids, for example, are what we call miscible in one another. They will mix in any proportions. That's like ethanol and water. The polarity of ethanol, which is also known as grain alcohol or drinking alcohol, its polarity is similar to that of water. They're both polar molecules, so they end up dissolving in one another, mixing in any ratio. If you end up with two liquids mixing with one another, well, as soon as they mix, we're not really looking at layers anymore. So sometimes we'll use nonpolar things like corn oil and polar things like water because we consider them immiscible. They don't dissolve in one another. And then you can make density columns a little more readily. Now let's consider two other liquids that are immiscible in one another. Let's look at water again. Like I said, it's polar, so it doesn't dissolve very readily, very much of a nonpolar substance. Let's consider a nonpolar substance like the hydrocarbons in fuels in our society. So gasoline is actually a mixture. It has many different carbon and hydrogen containing molecules called hydrocarbons. Okay, if we consider gasoline though, it's a liquid. The water's a liquid. They're not miscible in one another, so I say they're immiscible. We're going to find that we would layer the two liquids if I were to spill gasoline on water with the lowest density at the top and the highest density at the bottom. Now, many of you may have on occasion enjoyed an action movie. If you really enjoyed an action movie at some point, you may realize that if you spill gasoline or jet fuel or many other types of fuels on top of water in a lake or in the ocean, that it layers on the top of the water. Okay, so if I spill gasoline in the lake, well, it's going to layer at the top, which is very helpful if you think about those handy action movies that some of you might have enjoyed, where often there will be a hero or a heroine that will go ahead and dive under the water because they will protect themselves from the burning gasoline potentially that could be ignited on the surface. So if I end up with burning gasoline for an action movie, well, we know that its density must be less than 1.0 grams per milliliter for the gasoline itself. And if we look at gasoline, well, it depends on the grade of gasoline we have, but it can have a density between 0.71 to 0.77 grams per centimeter cubed. Okay, so with that in mind, since gasoline is a nonpolar liquid, it's not miscible in water. If we had gasoline spilled on water and lit it on fire, well, it's going to stay on the surface, and that's where your hero could dive underneath, and as long as they could hold their breath and swim far enough, they potentially could swim beyond the non-polar gasoline and come to the surface safe and sound. Okay, so that's something interesting. So there's density and thinking about action movies, kind of useful. Now, other density calculations we'll look at will involve more than just comparing density values to determine how density columns would layer or how one immiscible substance might layer on top of another. Okay, we're going to be using our formula for density, and we're going to say, well, density is equal to mass over volume. If I have that ratio, well, I could say if I know mass and if I know volume, I can take the mass divided by the volume, solve for the density. So I could set up this type of solution map where I take the known information and find an unknown variable. Now, I should be able to solve for any of these variables, though. So let's say if I want to solve for volume. Now, algebraically, if I want to solve for volume, I multiply volume on both sides of my equation so that volume will cancel, and I'll get volume times density is equal to mass. Okay. Or if I wanted to isolate that volume, I could divide by density on both sides then, and then end up with volume is equal to mass over density. So that's what I've done here. So I can go ahead algebraically and solve for volume. So make sure you can do that. If you need a little bit of help, please talk to me or your instructor there at your location. Your volume is going to be equal to mass over density. So if I know mass and density, this is the equation I would use. Now you can either memorize each of these equations I'm giving you, or just be very comfortable with doing the algebra and memorize the first relationship of density is mass over volume. Now if I consider that my mass will be equal to my density times my volume, I could solve for the variable of mass. Okay? To determine that, all I did was multiply both sides by volume, right, to isolate mass. So these are the three equations we will commonly use. Now we may still have some metric conversions with metric prefixes that are involved in some of these calculations, but here's all we have to do for a density calculation. They're very simple calculation. So let's consider a few scenarios like this. Now density can be used as a conversion factor. Let's see what I mean by that statement. If density is a conversion factor, well then we can write down a few densities and see how they could be related to one another. So let's say that the density of water is 1 gram per milliliter. Well, I could write a conversion factor that shows 1 gram of H2O is equal to 1 milliliter of H2O. Okay. I could also look at the density of lead, which is 11.3 grams per centimeter cubed. I could say, well, that's the same as considering the relationship that if I have 11.3 grams of lead, that would mean I had 1 centimeter cubed of lead or 1 milliliter of lead. right? So I can write these nice conversion factors with densities and then use them in calculations that involve density in my dimensional analysis. So let's do an example of this. Let's say that we would like to know how much 4.0 centimeters cubed of lead would weigh. So I have the volume of the lead. Okay, I would like to know the mass of the lead, and since I can easily look up the density with the given information for lead is 11.3 grams of lead for every 1 centimeter cubed, I could use this conversion factor from my density to determine the mass that I had as long as I had the volume. Okay, so I need to recognize which one of my equations I need to use. So we need to solve for mass. So mass is equal to density times volume. So I could go ahead and write that 4.0 centimeters cubed of lead. That's my original volume that was given. I can multiply that by density, the 11.3 grams of lead for every 1 centimeter cubed, and we would end up with finding that I had a mass of 45 grams. So 4.0 centimeters cubed is 1 centimeter cubed is 45 grams here in this calculation. I want you to notice that it's fairly easy to do this. The centimeters cubed cancel, and I end up with having grams for my units after all. At the end. Now I can take any volume of lead and plug them into this equation times the density to find my mass. So that's a very common type of calculation that we would do. Let's do another similar type of calculation. Let's consider that if we were interested in the mass, in the volume in centimeters cubed of gasoline that would fill an automobile gas tank. Well, if I know the mass of the gasoline and if I know the density of the gasoline, I could easily find that volume. Okay, so the mass of gas that would fit into this automobile engine is 60.0 kilograms. The density of the gasoline that we're using is 0.752 grams per centimeter cubed. That should look familiar compared to the gasoline density ranges we looked at previously. I'd like to solve for the volume in centimeters cubed. So if I first of all imagine that density is equal to mass over volume, I can multiply both sides by volume and divide both sides by density in my equation to generate the following equation. So volume would be equal to mass over density. Okay. Now when you're working these types of problems, or any type of calculation in this course, it's very useful sometimes to write down the given information that you have. So here we were told that we have 60 kilograms for the mass of the substance. We also know that we need to find the volume in liters. Okay, so if I go ahead and plan out my calculation here, I'm going to start with kilograms, and I need to convert from my metric prefix of kilo to grams. So I'm going to go ahead and say there's 1,000 grams for every 1 kilogram. Okay, that will go ahead and determine the number of grams I have with a metric conversion. Once I get to the number of grams, I can put my mass in grams and divide by my density. So I would divide by 0.752 grams per 1 centimeter. Notice I'm using density as a conversion factor, but here I had to invert it because I'm dividing by it. Now that would give me my number of centimeters cubed. Okay, so we have a few conversion factors we're using. We're using that conversion factor of 0.752 grams for every 1 centimeter cubed. We're using conversion factor that 1,000 grams is equal to 1 kilogram. So there's my conversion factor from the metric system, and there's my conversion factor from density. Okay. So that's what I'm doing. I'm converting from kilograms to grams to centimeter cubed. So here's how I would set up the dimensional analysis on my paper. I'd say that 60 kilograms would be multiplied by 1,000 grams per 1 kilogram to convert to grams. So there's my metric unit conversion factor. And then I'm dividing by density. So 1 centimeter cubed is divided by 0.752 grams. Okay, you'll notice that my kilograms will cancel, my grams will cancel. I'll end up with centimeters cubed, so I get 7.98 times 10 to the 4 centimeters cubed. Okay. Now, what if we have a substance that is hard to find the volume of? Now, it's very easy to determine the volume of some regular shaped objects. So if I have a cube or a sphere or a cylinder, I can use the geometric equations for cubes, spheres, or cylinders, or rectangular objects, let's say, to calculate the volumes by measuring the dimensions of my object. Now, not every object, though, are these perfect shapes, like spheres or cylinders. However, there are ways to determine the volumes of those irregular shaped objects. Now, the history behind this really originates from a very famous mathematician, Archimedes of Syracuse. He was well known for his ability to determine volumes of objects. And the king of Syracuse at the time period had a crown, as the story tells us, commissioned. Now, the crown was made out of gold and has an irregular shaped parts of the crown, which made it not easy to measure the dimensions of and calculate the volume. And the king was worried when he gave the gold to a jeweler to make this crown that potentially the jeweler had kept some of the gold for himself. Now, the king was definitely able to measure the mass of the crown, but he knows jewelers can make alloys with gold, and that some of the gold may have been replaced with other metals that were less precious. Now, because he had the mass, and it appeared to have been the same mass as the amount of gold that he'd given the jeweler, he would have needed the density be calculated to see if it matched gold by looking at a mass over volume ratio. So we needed to see if the volume was the same as the pure gold that they began with. Okay. Now, he gave this problem to Archimedes. He said, can you find out if this is pure gold with this crown? Now, we can imagine perhaps Archimedes had said, let's go ahead and melt the crown down and make a cube or a sphere out of it, and it'll be really easy to calculate if it's the right volume compared to the volume of gold you originally gave him. You can also probably imagine that the king said, well, wait a minute, I just went to all this trouble to get the crown made. I don't want to melt it down. So he said to Archimedes, most likely, you can determine if this is pure gold, but I don't want you to damage the crown in any way. So you can imagine, just like if your chemistry instructor had told you, here's a really hard problem to work on, and maybe you needed to relax because you'd had a stressful time working on your chemistry homework, you might go somewhere to relax, maybe soak your bones. So let's say around here you might decide to go to Miracle Hot Springs and soak for a while and think about your problems and try to solve the tough chemistry problems that we've assigned you. Well, Archimedes perhaps was doing something similar to this. He went to the public baths of the time period and decided to soak in the tubs, and as Archimedes dipped his body into the tubs of the time period, he noticed the water level rose, and he realized that he was displacing a volume of water equal to the volume of his body. Now, water will take on the shape as a liquid of its container. So if he were to fill the tub to the top and then submerge his body in there and collect the water that spilled off the sides, he could definitely find that volume of water was equal to the volume of his body. So he could find the volume of an irregular shaped object, right? His body was irregular in shape. Okay, so that's where this would be quite useful. Now, as Archimedes was considering this, he realized this was his solution to the crown. If he could submerge the crown and see the change in the volume of water level, that would be very simple in order to find the volume of the crown itself without damaging the crown. Now, supposedly Archimedes was so excited about this revelation that he could find volumes of objects by what is called volume displacement, that he supposedly ran out into the street naked yelling, "Eureka, Eureka," which means I found it, I found it. Okay, now I'm really hoping that all the students in the course get very excited about determining volumes by volume displacement, but please keep your clothes on. It's really not acceptable for you to run around the classroom or the lab naked. So keep your clothes on. You can be excited as you want, but don't strip down. Okay, now unfortunately we don't know the end of the story. I have found no location where there's actually a documented record of whether the crown was pure gold or not. So I can't tell you if that's true or not. I suspect that if you run into stories that give you the end of that, it's maybe been made up after the fact. Okay, so we don't know the end of the story, but this is definitely a way they could find out the volume of the crown. Now let's imagine in the laboratory, if you're dealing with smaller irregular shaped objects and you want to find their volume, what could you submerge them in to measure a volume change? Well, I'm hoping you're thinking maybe a graduated cylinder, right? My graduated cylinders will have certain milliliter volumes that you're dealing with. If I take an irregular shaped object and I measure the volume of water in a graduated cylinder, submerge the irregular shaped object in the cylinder. Now be careful to tilt your cylinder and gently allow the irregular shaped object to slide down the side of the glass, because if you have a heavy piece of metal that you put in your graduated cylinder, you could break out the bottom of the cylinder and have water spill out. You won't get a good measurement that way, and you just destroyed the cylinder. Okay, so I gently put that object in case it has a high density and might break the glass. And once it's submerged, the water level will have risen. So I go ahead and put the graduated cylinder upright again, get my eye at the same height to avoid parallax error with the reading, and then we can see that where the volume was at the end versus initially, I can take the volume final once I submerge the object minus the volume initial before I put the object in the water. We'll be able to find that change in volume is the volume of my irregular shaped object. I can also determine the mass of my object by maybe using one of the scales in the lab. I could take the dry object, determine its mass on the scale. With those two numbers, the mass and the volume, I can find a density, even though the volume couldn't be measured easily to find the volume of the object. Okay. Now, one of the things when you're doing this, you have to be very careful not to splash your water when you submerge the object, because if you lose any droplets of water, or if you have droplets end up adhering to the glass further up on your graduated cylinder, that would cause you an error. Okay, so that's something to think about. Now, let's say you are going to take your knowledge of volume displacement to solve a problem. So let's consider that maybe you are dating somebody and they give you a ring. Perhaps they're proposing. In that case, when they give you that ring, they tell you that they got a really great deal on it. It's a platinum ring, but they got this really great deal. It didn't cost them very much. The jeweler did a great deal for them. That may make you suspicious because you know platinum's very expensive. So you may wonder if maybe it's an alloy with platinum and another metal, or if perhaps you have a metal other than platinum present, or you have maybe electroplated platinum on the surface of another metal, so there's very low platinum there. Now, in order to determine if your significant other has given you a high carat value of the platinum ring, or if perhaps they've given you another metal. Now, they may have done this on purpose or maybe on accident. So we need to know, well, was it the jeweler or was it the significant other that's giving you the ring that might not know what the metal is or maybe try to fool you? So in this case, this student happened to know how to use volume displacement. So they took the mass of the metal ring. Now we'd have to have no stone there, or we'd have the density of the stone averaged in here. So I just have to have a regular band. But I can go ahead and take the mass of just the metal ring on the scale in the lab. And if you understand, you could use a graduated cylinder to submerge the ring and find the change in volume. You could determine its density. Okay, so let's go ahead and pause the video and do this calculation. So we have a mass of the ring is 5.84 grams. Okay, it displaces when I submerge it, so I already found the volume final and volume initial. That difference was a little more than half a milliliter, so 0.556 centimeters cubed. Okay, remember 1 milliliter is 1 centimeter cubed. I told you the density of platinum is 21.4 grams per centimeter cubed. I'm only using the density of platinum to make a comparison here, right? So if you pause the video and try this calculation, I want you to try to determine if A, yes it is pure platinum, or B, no it is not pure platinum. Okay, so try that right now. Okay, so when you did this calculation, it was a fairly simple calculation. I took the 5.84 grams of my ring mass. I divided by the volume of 0.556 centimeters cubed. Hopefully you did that. What answer did you receive? Was it the same as a density of 21.4 grams per centimeter cubed? If you calculated this correctly, you should have said no, it's not pure platinum, because your calculation should have given you a value of 10.5, so 10.5 grams per centimeter cubed. So it's quite a bit less dense than pure platinum. So this ring could not be pure platinum based on the data we collected. So we could compare densities of different substances, say on a chart, to see what substance we might have here. So I go ahead and I realize I have a density of about 10.5 grams per centimeter cubed. Well, that would be close to silver. So it's possible that this ring is mostly silver. Now, some of you may be saying, well, the platinum's density is 21.4 grams. But if there's another metal present in an alloy, well, that could throw the density off. Well, let's think about some common metals that can be present in platinum jewelry. Well, iridium's used frequently, but its density is actually higher than platinum. So if we had platinum mixed with iridium, our density would have been close to that of platinum or a little bit higher. So that doesn't fit the bill. So I probably don't have very much iridium here in any alloy present. Other metals might be ruthenium, but notice ruthenium's density is quite a bit less than platinum, okay? But it's still not as low as that of silver, so I would have had some density in between 12.2 and 21.4, so it doesn't fit that it's just ruthenium there. Now, it is possible maybe that a large amount of it could be cobalt, which has a density of 8.9, but if it is, there's not much platinum there. There's quite a bit of cobalt present in the alloy. So it looks like this ring definitely isn't as good of a deal as maybe somebody thought it was, or somebody's trying to fool you. Maybe the jeweler, maybe the significant other. So we definitely have less value than a pure platinum or a high carat value of platinum ring would contain. Sorry about that. Hopefully if you ever did this, you'd have better results. Okay, so that's kind of an interesting way to calculate densities. Let's consider another density calculation where we're going to do a conversion with respect to finding not only the mass here in kilograms, which is given, but the gram quantity. So you notice I'm converting from kilograms in this calculation to find gram quantity. So first of all, here's the question. A small fishing vessel weighs about 16,000 kilograms. If the vessel is made from iron, what volume of iron would it consist of? Now, I want you to report your answers in meters cubed. So we're going to have some unit conversions that we have to look at. We're also going to be converting metric prefixes and using density. Okay, so I'm going to go ahead and set up these calculations and take a look at this here. And so if we consider that we started with 16,000 kilograms, just a second. And in fact, this would be a very good problem to pause and try to work on your paper to see if you're getting the same answer as me. So you might want to pause this and then try working it on your paper and see what answer you get. Okay, so first of all, we're beginning with the 16,000 kilograms. So if I start with the 16,000 kilograms, whoops, if I can get my pen to work, just a second. Whoops. My pen just doesn't like me today. Okay, so if I start with my 16,000 kilograms, and I convert that to grams, I need a metric conversion here. So what's my relationship between kilograms and grams? Well, hopefully you recognize that we would have 1 kilogram containing, so I divide by kilograms to cancel my units, 1 kilogram contains 1,000 grams. Okay, so if I take 16,000 kilograms times 1,000, we're going to get a fairly large number. I'm going to report it in scientific notation. Now, the 16,000 kilograms, in this case, would have had 5 significant figures since the decimal point was shown. If the decimal point wasn't there, we would have had 2 significant figures. Let's treat this as if there was only 2 significant figures in the original number. So if I write that in scientific notation, it would be 1.6... have a decimal point there, times 10 to the 7th. Times 10 to the 7th grams. So I have a fairly large number of grams because I had 16,000 kilograms to begin with. So scientific notation is a little more handy than writing the 7 digits out. Now, once I get the number of grams here, I could use my density as a conversion factor. So if I'm thinking about my density here, I have 7.9 grams for my density would be equal to 1 milliliter, or 1 centimeter cubed of the iron. Okay, so there's a conversion factor I'm going to use. So since I want to convert from grams to a volume, perhaps we should convert from grams to number of milliliters. So I'm going to go ahead and use my conversion factor to do so. So I need to cancel grams out, so I'm dividing by 7.9 grams, 7.9 grams for every 1 milliliter. So my grams will cancel. I'll end up with milliliters. And so my volume then in milliliters, now I'm not quite at my final answer because I want to convert from milliliters to meters cubed in a moment. But my volume in milliliters would be 2.0. And I know I told you to only keep track of this as if there were 2 significant figures, but I don't want to round yet, so it would be 2.025316, right, times 10 to the 6th. So you can go ahead and write all the digits down to keep track of them in that calculation, times 10 to the 6th. Okay, that's how many milliliters I have. Now, I can also compare this to centimeters cubed by recognizing that 1 milliliter is merely 1 centimeter cubed. So I divide by 1 milliliter for every 1 centimeter cubed. It's the same value, right? So there wasn't much of a change there. Absolutely the same value. Okay, now if I wanted to convert to meters, well, you might recognize that there's an almost useful conversion factor. If I recognize that for every 1 meter, there's going to be 100 centimeters. Now that's pretty useful, and it would relate centimeters to meters. Now unfortunately these are lengths, right? And I have centimeters cubed here and meters cubed that I want to convert to. So I can't just use lengths. I need a cubic conversion factor. Now you don't have to memorize the cubic conversion factor from meters to centimeters. You can merely realize that if I have 1 meter here is equal to 100 centimeters, if I want to convert that to a cubic conversion, I just cube both sides. Very simple. So I cubed the 1. Now, I cubed 1 is just 1. Even though cubing 1 is still 1, cubing 100 is not still 100. So you must remember to cube the number on both sides. Plus you should cube the unit. So I have meters cubed if I do this and centimeters cubed. So there's my useful conversion factor for cubic conversions. I made the almost useful conversion factor into a much more useful conversion factor. So I can continue my calculation here. I can say, okay, for every 100 cubed, so take 100 cubed, centimeters cubed. Now remember, if I want 100 cubed, I just take 100 times 100 times 100. Your calculator should have a function where you could take x to the n or some similar type of function. Some calculators have a y to the x, so I could put 100 in, hit that y to the x, and put a 3. That would go ahead and say take 100 times itself, right, 3 times. So 100 times 100 times 100. So I have 100 cubed for every 1 meter cubed. So my milliliters would cancel units, my centimeters would cancel, centimeters cubed would cancel, and I end up with meters cubed. So the answer to this final calculation would be 2.0 meters cubed of iron used in this fishing vessel. So we were able to do a pretty fun calculation here. Not only did it involve metric conversions with respect to the kilograms to grams, but we also were able to use scientific notation to keep track of things, to make it a little easier to write everything down. Now realize I normally wouldn't round to significant figures at the very end, but for sake of space here I did. Not a good practice. I would have kept track of all those all the way through. Then I converted from my grams though to milliliters by using density. So this is the new thing you're doing right now, using density as a conversion factor to go from a mass to a volume or a volume to a mass. So here I went from mass to volume. Once I had the number of milliliters, though, we had a unit conversion. I had to go from milliliters to centimeters cubed. Then I had to convert from centimeters cubed to meters cubed. You will have questions on your next exam which will involve all of those types of conversions, so please do practice them. Okay. That gives us the final answer. Now, I do like it in your tests if you botch your final answer, okay, as you're reporting these. Okay, so this is a good place I think we should stop today, since you probably took a little extra time doing a few of the calculations. Next time we'll look at a few more density calculations and some temperature conversions, and then we'll practice a few more conversion problems that are a little more challenging. So that's what's our plan for next time. Okay, thank you very much. Have a great day.